So, welcome to the fourth lecture, everyone. Again, this is Human Motor Control and Learning. And in today's lecture, we're actually going to get into the motor control theories and discussing sort of the involvement of the different sensory processes that we have available to us while we're performing motor skills. Now, before we get started, I just wanted to discuss the news from today about the strike. The strike is for full-time faculty, and in that regard, this course will not be affected. The other course that I teach as well, some of you are in it, Intro to Movement Neuroscience, that course as well will not be affected. And so the way that the course is running prior to the strike would be the same. And so that would include the synchronous online lectures, the quizzes, the assignment, and then the in-person labs. Will all remain the same. The one thing that would affect you potentially is just that it may take longer to get onto campus with the potential of picket lines. So just accommodate for that. Now, remember, with the labs, you all will be going into lab for the week one. So lab 2 is this week, I believe. You all will be going in for week 1. If you complete it this week, then perfect. And if you need more time, you can always go back the following week, so next week. Does that make sense, everyone? No strike. So I guess the benefit of this would be at least now you'll have some classes that are on hold while you can focus in on some courses that are not. And then kind of separates the amount of workload that you have. Georgia has a question. She wants to know when the labs are due. Someone want to let her know? Yeah, Canvas. So I'll just repeat it. That's really funny. Canvas says 11:59 just because I wanted to. If not, then I would have to go individually which labs you're in and set the due date. So I put it at the last available time of that day. You have to hand in the lab before you go into lab 2. So then when you go in, the TA will know that you didn't hand it in. It just makes it easier than for like scheduling on Canvas. I would have to go one by one. And I don't know how to check your lab times individually. But that's fair, yeah. Again, if you have an issue with like submission, always email your TA because they may be able to allow you to email them directly, of course. So is everyone okay with labs this week? Are you all excited? It's a shame that with the semester again and the strike now, there'll be maybe a little bit more problems. But the good thing is that in regards to this course, nothing will change as of the change that we made 2 weeks ago. Okay? Appreciate you all bearing with me. And I appreciate you all, or I hope that you appreciate me bearing with all of you. We're sort of all in it together. And as long as you're learning the course material and finding it enjoyable and applicable to the things that you see in your daily life and in like moving forward in your careers, then I'm doing my job. Thanks, Partis. So ready for the lecture? Today we're going to be learning, like I said, about the different individual motor control theories. So we're going to introduce the idea of, oh, hi, Karen. I'm going to introduce sort of the basis of how we developed our motor control theories, sort of the variables and factors that they had to figure out. And then we're going to go into how individual sensory processes are incorporated in our motor program or in our motor control as we perform different motor skills. So remember, motor control research is looking at the sort of function of the body's ability to perform motor skills under varying conditions. So you could perform something that you've learned under novel conditions quite readily. Like our body is able, or our brain or neuromuscular system is able to process all of that information very quickly. When analyzing motor control from a study perspective, and we learned about sort of some of the history already in the course, and we're going to continue on with. Oh, I hear feedback. That was Karen. Good job, Karen. She was trying remixing. So automatic means that you have no attention. Like when you're doing something, you don't have to have any attention on it. So not everything we do is automatic, but it becomes easier and easier. The motor control theories wanted to look at what is the command that our brain is developing. What's the nature of the command? Like, is it just the list of muscles that we're contracting, like I described last day, or is it the incorporation of the environment and then the stored motor program? Like, is the motor program the automatic part, and then what's available to us is sort of added to the automaticity of the motor skill? They just didn't know, right? And they wanted to sort of use these theories to be able to understand what we visually see is that people that are good at a motor skill are able to do it accurately and consistently under a whole bunch of different conditions. Like think of like a professional athlete. They're able to complete that sport in a wide range of different conditions. And so how does that work? Or what's the sort of neurological or neuromotor basis behind that? So to develop a theory, what you do is you do a bunch of research and you observe sort of the factors. You observe what's going on, and then you take that information. You're able to make predictions about future observations, and that's how you develop a theory, regardless of what field it's in. And so, for motor control theory, like I had said in the first lecture, that it started off from sort of analyzing motor control or motor skills from a psychological behavioral level. Motor control theories wanted to make observation of people performing motor skills from a behavioral level. And so the two questions that they needed to sort of describe or to incorporate in their theories is what we've already just talked about. That one, how are we able to coordinate our bodies? And then two, this degrees of freedom problem. So degrees of freedom just means the number of independent elements in a system. So if you think of, like robotics, the degrees of freedoms are how many axes a joint can move, for example. When we're talking about motor control and the degrees of freedom problem with motor control theories, we're talking about using the theory to sort of develop a idea on how we're able to control so many independent elements all at once. And so if we think of how many independent elements or how many degrees of freedom are in our bodies when completing a motor skill, let's look at all the different joints. So a common example of picking up a cup of coffee. So it's not that I just have to control one joint. I have my shoulder, my elbow, I have my wrist, I have all of the individual joints in my phalanges and the metacarpals, plus my thoracic spine. There's so many independent elements. So if you think of the body as like a puppet, look how many strings would be required for just even the simplest movements. How is our body able to coordinate the movements of all of those different joints? It's a lot of information. And so they wanted to develop theories on how the body is able to simplify that or coordinate or process that. And so the one question the theories had to do was answer this, the degrees of freedom problem. The second thing was the coordination of our body as it pertains to motor skills. And so what that is defined as, it's not just coordination of that person looks coordinated or they're fluid when they're moving. When talking about motor control theories and discussing the term coordination, it's defined as the patterning of the body and limb motions relative to the patterning of the environmental objects and events. And so what that means is, how are we able to coordinate our bodies in relation to the environment in real time? So coordination, when it relates to motor control theories, is talking about how we're able to take a motor skill and adjust it for, the situation of the environment in that moment. So think about, you're a basketball player and you can shoot really well. Well, you're able to shoot when there's a defender, and if you're different distances from the hoop, or if you're running, if you're not, if you're off balance, all of that information, wherever like the people are guarding you are, all of that information is added to your motor skill, and you're able to adjust it or coordinate your body based on those situations. Does that make sense, everyone? Because it's not just being able to, like, if you think about it itself, learning how to control our bodies is just one piece of this crazy ability that we have. How are we able to how are we able to move our bodies so efficiently and so consistently? And then how are we able to do that under like varying conditions all the time and in a split second? It's amazing. So, motor control theories described that. So there's a whole bunch of different theories, and then a lot of them came together. There's two main theories. There is the motor program-based theory and the dynamical systems theory, and we'll get into what those are. But both of those theories and all of the theories that sort of developed through this research from the 70s and on had to describe that the motor system was able to work in both an open and closed loop system. So that just means that we could work with or independently of feedback. We talked about one of the biggest sort of observations that researchers and everyone sort of realized in the beginning stages was this whole idea of the speed accuracy trade-off. What is something that we notice with movements as we try to perform them more accurately? Slower. So that just means that we're more dependent. We're moving slower because we're putting more reliance on taking feedback and adjusting our motor skill, whatever we're doing, in real time. Whereas if you do things quicker, there's not enough time for feedback. So all of the instructions from the brain have to incorporate all of those movements without the use of feedback. So we're going to talk about the difference between open and closed loop systems. And we're describing how the brain, or the central executive, how that changes the instructions that could potentially send out to the body. And because we can see that both are, depending on the situation, your body may choose one or the other, the theories will have to incorporate our ability to use both. So let's first talk about closed loop systems. Closed loop systems are dependent on the use of feedback. So if I'm doing slow, what would be the nature of the instructions that the brain would have to put together to start movement? If our motor system is working in a closed loop system, that means that the brain, the initial instructions will just have to be enough to initiate movement. And then because we're moving slower, there's an ability to keep taking in feedback from our sensory processes, whatever they are, like if there's visual, auditory, touch, proprioception, whatever ones are important for that motor skill. We're able to take that information in real time and adjust our movement in real time. So the amount of instructions that are required to get moving in a closed loop system is a lot less. Whereas if we're moving very quickly, there's not enough time. Like think about like flipping off a light switch. You're not moving slow, so you can figure out how much precise pressure is required for the light switch, and then you stop slowly so that way you don't like hit the end of the plastic when you're moving. If you're moving quickly, there's not enough time for taking in feedback and adjusting the movements. And so in this case, in an open loop system, your motor control is independent of feedback, and therefore what the brain is sending out to the muscles has to contain all of the information required or necessary to carry out the full movement from start to finish. And so looking at a diagram, here we have what the difference would be between an open loop or closed loop system. Now remember, all the different motor theories had to incorporate the fact that our neuromuscular systems can both work in an open and closed loop system depending on the situation and different variables. We've talked about speed or accuracy. And what are some other factors that could be a factor in whether or not our brain is going to send out instructions in a closed or open loop fashion? Any ideas? Just the next slide. So if we want to move more accurately, or we want to move with precision, would we want to work in an open or closed loop system? Because we can all agree on that, right? Because it allows you to take feedback. So that would be vision, touch, maybe proprioception on how you're moving your hand, whatever we've decided to need to accurately. But it's allowing you to sort of adjust minutely in real time and become more accurate. Make sense? Try to draw very quickly versus draw slowly. Someone who said Pardis was talking about automaticity, right? Like if something's automatic. It's okay if you can't draw because you're all a work of art already. So Pardis, what about this idea if something is learned very well or learned very not well? So if something's new versus if we're doing something, a motor skill that we've learned very well, maybe that's a factor in whether or not our body can use an open or closed loop system, right? Yeah, new is not as coordinated. And so maybe with learning, we would have to work in a closed loop system because remember, when we are learning, we can't rely on our proprioception as much because we're not like familiar with the movements of our bodies as much, right? So maybe with a newly learned skill, we work in a closed loop system. And then as we get better and better and better, we rely less on feedback and we can now move in a open loop system. Does that make sense, right? So the transition from new to well learned, you're moving from closed loop to open loop. And then remember how we were talking about like the classifications of different skills, and then before Gentile's two-dimensional taxonomy, there was those one-dimensional systems. What was the difference between a continuous or discrete skill? If anyone can answer. Right. So, yep, you guys are all right. So think about the differences, and maybe there's a difference in the type of system we would utilize if the task is different. So maybe in a continuous skill, because it's repetition, 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 maybe we're working in a closed loop system. So you get the system going and then you're adjusting minutely. Like think about running. You're not thinking about every step. You're probably like many runners. You're running and then you realize your hamstring's tight or you're putting more pressure on one side versus the other. Little differences. Maybe that is working in a closed loop system. Whereas if it's a discrete skill, quicker, distinct beginning and end, maybe in those situations, your body prefers to control itself in an open loop system. So the point of this little bit of the lecture was just reiterating that the theories that the different researchers had come up with had to incorporate our ability, or the neuromuscular system's ability, to work in both an open or closed loop system, and determine the difference in why the body would choose one versus the other. And we've come up with a good number of reasons right now, and they all sort of make sense. So have you had any experience with any of these theories before? I believe dynamical systems theory is discussed in Megan Lowen's course. Okay. We'll review it. I don't think I think she goes more into depth about it. This is more about how it relates to the control of the body in different situations. But the two main theories that are out there are the motor program based theory. This was the original one. And then there's the dynamical systems theory. The motor program based theory is thinking that for every class of action, so every type of motor skill, it's defined by certain variables, but we have like the memorization of that program. So think of like motor program as like a computer program. And what part of the body or the brain would we be storing each of these motor programs, do you think? We talked about it last time. Cerebellum, yep. The dynamical systems theory is still talking about this idea that we have a memory based of, the specifics of a motor skill in our cerebellum, except what it states that if we get the body moving, sort of the patterning of the body sort of the body sort of randomly moves in a fashion with that's predicted by like the moving elements. So if you just start moving your hands, or sorry, your legs when you're running, the motion of running sort of just like sort of happens. I don't know if that was a good example at all. But what the dynamical systems theory suggests is that the amount of instructions that our brain has to coordinate or process is less. It just has to get the body moving. And then with feedback and sort of reflexes and all of the sort of control at a lower than brain level, the patterning of the body or the movements and the coordination all sort of like comes together. So the dynamical systems theory is just a sort of way to suggest that the amount of instructions or processing the brain has to do is less than was suggested in the motor program based theory. The biggest con or like knock on the motor program based theory is that us having to memorize different program for every motor skill we've ever learned, it just seems like a lot. And so Karen's saying, so with dynamical systems theory, it's if things are in rhythm, a sort of like pattern sort of emerges. That's dynamical systems theory. Yes. So let's first start off with the original one, and hopefully you're all not too confused. Motor program based theory is just based on this concept of a motor program. It was developed in 1988, and what it suggests is that for every class of action, we have a generalized motor program. And this is what is stored in memory. So whether or not it's in like our conscious memory or in our cerebellum, and then we developed an understanding of what the cerebellum was as this information was coming to light. But this is what's stored when we learn something. When we learn a motor skill and never forget it, we're learning the motor program. And so we've accumulated throughout our life a motor program for every motor skill we've learned. which makes sense, right? Except when we think about all the different things we're able to do, it's a lot of information. Right? So then people were trying to study this and be like, how does this even make sense? Like, how could your brain just memorize everything? Especially if you have to control every little individual joint of your body. How does your body memorize all that? Okay, you got to flex all these muscles in this order. But taking the theory as it was being developed, this motor program based theory, it would suggest that the motor program is responsible for creating the instructions of that motor skill completely for generating all of the instructions required. Yes, and so so then how they would look at, so Karen's saying, so your body could remember all of that if it was highly organized. And then they wanted to know, okay, well, what is memorized then, and then what's added on? Because remember, our body is able to take a motor skill. So let's say we're just solely motor program. You take a program, but then you have to modify it for the environment in that situation. So then what is memorized and then what is added to it to allow us to perform that motor skill in that situation? The way that they described what would be sort of stored in our brain and what would distinguish different motor skills is, okay, so I can pick up this cup. If I pick up a mug, is that the same motor skill? Is brushing your teeth the same as drinking? Is that the same motor skill? So what's one motor skill that you're memorizing and what's not? So that what they would suggest is that each motor program that you've remembered is associated with a class of actions that have the same invariant features. And we'll discuss what that means, but they have the same sort of invariant motions. And then the environment or the sort of real-time variables that you would have to adjust your motor program for that time would be the parameters. Parameters are being added to the program to complete that skill in that real time. So it would, so they didn't know. That was the question. Is picking up a glass the same as a mug? Because the hand's a little bit different. Think of the invariant features as like an analogy of dance. So if you are doing a dance routine, so here we have an analogy of dance being like, does anyone know what the waltz is? Is that even still a thing? So waltz always has the same sort of movements, right? It has the same like time, right? The 3 beats. The tempo you can change. So you could speed up or slow down the waltz, it's still the waltz. So you would describe the rhythm as the invariant feature of a waltz. Whereas the tempo is what can change. That would be a parameter. Think about this example here. So think about this as like a TikTok dance. So it has like a different like dance moves. So you could do it slower or faster. So faster, slower, but see how the dance moves, the percentages of, the time spent in each of the different moves is the same. It's just either longer or shorter based on whether or not it's a faster or you're doing the dance slower or faster. So they would say then if this was a motor program, then the individual dance moves and the order would be the invariant features of that dance. And then the speed of how fast you complete the dance would be the parameter. It's difficult to comprehend then, just like Karen was asking. It's still kind of difficult to figure out, well, then what is distinguishing between two different classes of motion? So is picking up a cup the same as picking up a mug? Is that two different classes of movements, or is that the same movement and different parameters? Motor program, so to answer your question, motor program would say picking up a cup is a different skill than picking up a mug. And we'll get into it, whereas the dynamical systems theory suggests that would be one motor program. Motor program-based theory suggests it's two different ones. So let's look at this example. This is a kind of before biomechanics, but what they wanted to do was look at the gait cycle, or like the way that people walk at different speeds. Because what they could do is they could look at people walking at different speeds and look at how their body moves. And so what they found was that at different speeds of walking, the percentages of the limbs in like stance cycle, step cycle, stance, swing phase. Have you guys done like the gait cycle? Yeah. So depending on the speed of walking, it was still walking based on the sort of gait characteristics. So each speed of walking still had the same invariant features. But what happened was when they sped up the treadmill enough, people would transition from walking to running. And then running, it changed their cycle. So now the invariant features changed. So then what would the motor program-based theory suggest? That walking and running are two different or the same motor program? Different. Because do we all sort of understand this term invariant features? It's a way to describe the similarities between between different skills that are of the same program. Do we all feel comfortable with this term invariant features? Okay, great. Here's another example of invariant features. There was this study, and we'll talk about it again next day. But if I was to get, okay, so Karen or Nolan, let's see, like, so Nolan's asked a question. So like jumping and squatting are similar, but different. Yes. So, I would say the goal of squatting versus jumping would be different. They also look different. So that would be two different, like the invariant features of both jumping and squatting would be different. But what about jumping off of one leg versus jumping off of two legs versus jumping and twisting? Is that the same or is that different? Probably. Motor program-based theory would say it's different because the invariant features are switching. Whereas dynamical systems theory says that they would probably be similar. The body is still, the instructions are left to interpretation of what's available. Dynamical systems theory is just a way to say that the amount of instructions or processing that the body has to do is less. So it's the theories are all combined together. But think of this example of, or as evidence of a motor program-based theory. If I get Nolan or Karen to close your eyes and write your name with your left hand, your right hand, your teeth, your feet, you're gonna, if you look at basically, you know, the writing of it, you will have the same like handwriting. Someone try it. Yeah. Does someone want to, like, your handwriting style is what's stored in your brain. Someone try it. Has anyone ever realized that before? So that's evidence of our handwriting style, the way that we communicate with words. That's what's stored in our brain. So therefore, regardless of what limb we use to write, or draw or write, the visual of it is still the same. So that counts as the invariant features. Karen's an outlier. Well, they're probably not as obvious as you think, Karen. Like if you look, see, they obviously here don't look very similar, but if you like really, probably the way that they're moving, right, the way that they've chosen to write is similar. Yes, they're probably left-handed. No, they're right-handed. See. Okay, Jess, do it. Put your camera on. Let's watch it. Huh? But so then now does that help with understanding, like, for example, another example of invariant feature? So what's stored as a motor program, motor skill writing, that motor program is stored in our cerebellum in our brain. And then the parameter, what we're adding to that, is sort of the available muscles or what we want to write with. Kieran's asking if would a head injury affect it? And for sure, it depends on where. Jessica saying she said someone to do the example. She's asking. You're someone. So depending on that, like yeah, do it after class. So Karen's asking what would happen if someone had a head injury. So if someone had a head injury, it obviously would affect their ability, but it could affect their memory. It could affect, depending on what part of the brain or what the injury is. Maybe they have lost their primary motor cortex, or maybe they've lost part of their cerebellum. Maybe with their head injury, their neck is off. Like there could be a bunch of different reasons on how that would affect motor skills. So it's sort of too generalized to answer without a specific area. Unless you want to come up with a specific area. Does that make sense? Okay. So dynamical systems theory is the theory that you all were sort of introduced to in Megan Lloyd's class. But this whole idea is that once you get a system moving, patterns emerge or self-organize. And so basically, it removes the amount of instructions that the body has or the mind has to create to get motor skills. Karen said, what about fine motor skill from one hand to the other? What would have asked the question again? So I'm not sure how to answer that. So what about fine motor skills from one hand to the other? All of them. But if you had a problem with your supplementary motor cortex, you would have a problem with like the motor skill using like two hands at once. Point it this way: it's too generalized to say. Yeah, there has to be a part of the brain that you have to ask specifically. But think of it this way: if I learn a motor skill with my dominant hand, and then I practice. If I do that motor skill with my opposite hand, I will be way better at it. So, for example, with people that are going to learn to use prosthetics, before the surgery to like usually there's a surgery to remove the amputate like the limb that's going to be amputated. They have them practicing with the good arm or leg because it would speed up the learning because they're already taking in the motor skill program, and then the parameter is the limb available. Is everyone okay? Hopefully I'm not getting off too topic. But with dynamical systems theory, the idea is that the brain instructions that are getting the body moving, it just gets the body moving. In the program is less information that's stored, and then the pattern of motion just sort of emerges, and that pattern of movement is going to be more dependent on, like, think about all of the afferent information that affects our reflexes and the minor movements that are controlled at the spinal cord level. That all of that sort of minute change can occur without the instructions coming from the brain. So I have a video here describing dynamical systems theory. I don't think it's too long if we want to watch it. Oh, it's 12 minutes. So we can all watch that on our own time. I have a way better video than this one. But if you want to get a better understanding of dynamical systems theory and this whole idea of, emergence or self-organization of movement patterns, watch the video. One really good thing that the dynamical systems theory did is that they allowed for the analysis of sort of different variables when discussing what was observed in these different studies. So instead of describing different motor programs as invariant features, there's obviously different terms. In dynamical systems theory, they described a stable state of motion. So a stable state of motion that you would see as in a motor skill as an attractor state. And it was defined by, instead of invariant features, order parameters. So order parameters is invariant features, but order parameters is talking about dynamical systems theory, whereas invariant features was for motor program-based theory. And then instead of saying the term parameters as, the external environment in that situation, they would describe parameters as the control parameters in dynamical systems theory. This was one of the main, this is interesting. This was one of the main examples that they gave as sort of attractor states. So this is what they did. So I want you all to put your fingers on the table and you go back and forth like that. Okay. Now you're going to tell your body to alternate like this. Okay. Are we all doing it? Okay. Now go faster and faster. And then watch. And then eventually they just start moving together. You're telling your brain to go alternating. And then all of a sudden, it switches to they're going in phase. So, like, obviously, we didn't go in our brain, okay, now we got to go and now move together. It's the same instructions that are being sent out. And then they're saying that if you change the control parameter, which in this case would be speed, that another stable state of motion occurs, or another attractor state. So, patterns of motion sort of emerge. I mean, it makes sense. So the instructions being sent out by the brain is moving like this. And then as you change speed, the instructions don't change, but another state of motion occurs, another attractor state. Weird, right? So then another example of what we've talked about previously in the lecture, remember how we said that the motor program-based theory said that because the invariant features of walking and running were different, it's two different motor programs, right? Dynamical systems theory argues that the instructions of locomotion, of movement is the same. And if you change the control parameter of speed, your body will just transition from one movement attractor state of walking into running. Does that make sense, everyone? The pattern of running just self-emerges out of the changing variable of speed. So that would mean that our brain has to store less information. Yeah, so exactly, it just happens. Other studies showed this, that there was two, like so instead of walking, they did swimming, and there was a transition from, they told people to just swim like a certain stroke and then keep increasing their speed. And everyone at some certain speed, they switched their patterning of movement. So remember, in a motor program based theory, each motor program or each motor skill is defined by invariant features, and parameters are what are added to the motor program. Whereas with dynamical systems theory, we still have our stored information, but what defines a motor program or a individual motor skill is the order parameters. And as we can change control parameters, we get different attractor states. Okay. So review that sentence like 3 times, and that's sort of the point of understanding the difference between the two different theories. In actuality, it's probably both a little bit, right? But a lot of cool terminology came out of dynamical systems theory, also because it came out later. So here we have order parameters again, control parameters. Here was one cool example. So has anyone ever broken a leg or injured their ankle where they had to wear a cast or a brace? Okay, so if you are now walking with a brace, do you have to retrain your body how to walk, or does it sort of just happen? Yeah, right? So they're arguing that, what's stored in the brain is still the same, but because there's only certain now number of joints available, another pattern of movement just sort of emerges. Yeah, stairs are different. Or what about crutches? Right now, if you have to move with crutches, that I think is harder to start practicing because that's not similar to walking is still walking with a cast and not a cast. You just scoot. Parties would get just in a wheelchair and get people to move them around. So what the dynamical systems theory proposed is that this whole idea of muscle synergies, that the brain has a sort of stored information, and what's the muscles available are added and will all work together through a muscle synergy. If one's not available, others will take over. That whole process is called muscle synergy. So we'll be able to utilize whatever is available in our body to complete that motor skill. It also discussed this whole idea of perception action coupling. And so it suggested that there was a coupling of picking things out in the environment, or introduced this topic that like think about like hitting a baseball. You have to time your movements with the environment, but I'm not consciously thinking, okay, I need to hit the ball then, or when you're braking for a car, you're not thinking, okay, I should wait 10 more seconds. You kind of your body's perceiving motion or the environment, and it couples it with the motor skill that you've learned. So that would remove the amount of processing that our brain has to do. It couples our movements with what's being noticed in the environment. So if you are walking to, okay, so if you're walking across the street, do you walk and then realize there's a curb, stop, step over the curb, and then walk? Or do you just keep walking and then you just step over the curb? Like you're not consciously thinking of when I should step over? Tell me. Right. Yeah. So somewhere along the line, how does your brain figure out the timing of that? It's because it's coupling your perception of motion or whatever, like in this case, it's visual. You're automatically timing your movement to what you're perceiving. Whereas whereas the motor program based theory, right, because it's less dependent on feedback, they would suggest that you have a walking program and then you have a stepping program and then you got a walk program again. It's a lot of information that your brain has to keep processing. Dynamical systems theory is that your body is just saying go, and then it's going to perceive, it's less processing. Things just kind of happen. Karen is now, please don't trip over the curb. Yeah. So if it's a novel situation, you'll obviously have to think about it, right? If it was I don't know, it was something you hadn't experienced before, you would stop and have to think about it, because there would be a whole new thing you have to learn or consider. But dynamical, I hope this makes sense now. The dynamical systems theory is a way to describe that movements all just kind of happen, and it's less amount that we have to memorize. Again, with this perception and perception action coupling, there was this study where what they would do is they had people walk through a door, and they would each time they would narrowly decrease the size of the door. And so they would check to see if people, when they would if they weren't going to fit, they would walk sideways through the door, right? People didn't walk up and then sort of size it out. They would know instinctively when they would have to turn. So this whole concept of affordances means that we we understand our relative fit of our body with our environment. There's a sort of an awareness of how we fit in relation to the world around us. They did another study where they would have a stair height, and people have to go up the stairs, and they would increase the size of the stair, and then people would instinctively recognize when they would have to sort of climb up the stair, and they couldn't just step on it like a normal stair. Interesting, right? So in relation to clinical stuff, when we have stroke patients, they have to relearn all of this through repetition. So they won't understand how their hand fits with a cup, and whether or not the cup needs to be held with two hands, one hand. Will their hand grip around it? Will they have to hold with their finger? It's like they've forgotten all of that. Not on purpose, but that's what needs to be trained. Is everyone okay so far? I'm not going too fast. I get excited because this stuff fascinates me. It's so simple, but it's so interesting. And your body's able to do this in real time. You don't even think about it. So weird. So now let's talk about the different sensory components, because clearly what dynamical systems theory tells us, in all of the observations that we've talked about, right, in the studies, but also what we've all noticed in real life, is that you are consciously being aware of your environment, and it's automatically adjusting our motor programs or our motor skills, or influencing our ability to complete motor skills. So let's talk about how the different sensory processes that are available to us impact movement. So the main ones that we typically utilize are touch, vision, and proprioception. And we'll go through each of them briefly now and then watch a little bit of a video. But this sensory information is clearly important for us in completing motor skills that we've learned. And that sensory information would be utilized before movement to figure out how we should move. It could be utilized during movement to give us feedback. And it can be utilized after movement to help us, consider what we should do differently to achieve the goal better next time. Karen's saying, mind blown about how much we process without even knowing. Yeah. All in the background. Sorry. So let's first talk about touch and how touch influences ability for completing motor skills. So we all are aware that touch is sort of provided to us. So right now we're talking about sensory processes. We feel touch through our skin receptors. So mechanoreceptors, we talked all about them in neuroscience. Gives us pain, touch, proprioception, pain, touch, temperature, vibration. Right? These are all the receptors here. And then that information is input into the brain. So people wanted to understand, is the sense of touch required for all motor skills or just ones where you're gripping things? What about typing? So for typing, do we need a sense of touch? Yeah, probably. This was the question. No one knew. So all they would do is there was like 1,000 different studies of where people would just do different motor skills, or the participants would do motor skills, and then they would numb the fingers and see how it changed. So there's so many stuff. Does anyone have the textbook? So then you can read about more of the studies. But someone was talking about touch as keyboards. So remember how they were saying that you could have the laser keyboards? Okay, so that would you be able to type because now you're not touching anything? And so what research has shown is, yeah, it really affects us. So what they did was, here's I'm just gonna give you a generalization. So they found that when in the different studies, so piano, typing, pointing and grasping, it affected accuracy. Your body tends to remember endpoints. So without the feedback of touch to say, oh, that's the end, your body can't remember distance very well. Consistency, they found that when they did typers, that so how you were taught to type, without touch your hands would slide, and then the movement would be variable in terms of positioning. Timing is off. So this is some weird study, but they had people drawing a circle in the air and then drawing a circle where the top was touch, and it made timing more consistent. Probably just having more sensory process. Remember, it's more information, right? So it helps with the motor skill in general. And then, well, this one makes sense, but for grasping stuff and holding cups and things where you're holding things in your hand, you definitely need touch because it gives you feedback on how well you're gripping it. People would grip the cup and then not feel that they're holding it, and it would just fall out of their hands. That makes sense, right? Where's that? Oh no, it's just with one of each of these. Okay, so then what about the next sensory process, proprioception? What do we? Well, I've discussed it a lot thus far in the course, but what is one thing that one ability that we develop as we progress from new learner to experienced person in a particular motor skill. We can rely more on proprioception, right? The studies want to sort of look at and prove this. I brought up last day muscle spindles because that's our main proprioceptor. We also have Golgi tendon organs and joint receptors, but all of this information is utilized to give us feedback on how our body is moving in space and how we're positioned. They looked at sort of, okay, so this was a little bit difficult. So with tactile, you would just numb people's fingers and then you could do motor skills with it without touch. How can you do a study where participants do and do not have proprioception? So they looked at monkey studies where they would cut their dorsal column. So they would lose touch and proprioception. Sometimes they use tendon vibration. And I think there's someone doing vibration and neck movements in a study at Ontario Tech right now. Haley, who is the TA for one of my courses. Well, yeah. So Bernadette would be the her lead. Yeah. So a lot of studies used diabetic patients because, so remember, proprioception is the largest of the sensory fibers. They're the ones that are affected first with diabetic neuropathy. So you could use them in studies because it's the proprioception that's most affected initially. So these are some of the different factors or participants they used in studies. You can look up, I was going to post a paper. It's pretty wordy, but what it looked at was people and their ability. So in this study, what they had to do was they had to move. So they had like a stick and they had to move the stick in between 2 points, 2 distance points, back and forth. And then what they did was they did it with and without vision. And what they found was that when and they used someone with diabetic neuropathy, someone that couldn't utilize proprioception, what they found was that when they removed vision, the diabetic participant performed. I'll share it. I'll put it in the module. They performed significantly worse. So all that proved was proprioception is important, but if we have vision available, you don't really notice the deficiency because humans rely most on vision. But once vision's gone and we have to rely on proprioception, then it showed the problem. That also shows that as we learn motor skills, right, we're initially rely heavily on vision. And then as we get better and better, we don't have to rely on vision. We can rely more on proprioception. This was one study that also looked at tendon vibration, and they wanted to look at how accurate people would. So they weren't looking; they had to make circles, right? So then draw a circle, and it would create a consistent pattern. Now draw a circle when the arm is being vibrated, and then your proprioception is off. Does that make sense? Karen's asked a question. If sensory input is taken away, then we have to compensate with vision. No. So vision is sensory input. Sensory is all of what we're talking about. We will rely on vision if it's available first. And if that's taken away, then we have to do everything else. If touch is taken away, then we have to compensate with more vision. We rely on vision, then the other ones. And if vision's taken away, then we have to rely on the other two. If we take away touch or proprioception, but vision is available, we'll still be able to perform because vision is so much. We won't notice the deficiencies in our lack of touch or proprioception until vision is gone. Does that make better sense? Does that make sense, Karen? Boom. Awesome. If you have the textbook, you can look at what proprioception provided. It allowed for improved movement accuracy, timing in terms of the onset of motor commands, coordination of body and limb segments. That's what the vibration. Timing is so they had people with diabetic neuropathy patients and then like sort of like normal participants, and what they had to do was that they had to raise their arm and their leg at the same time based on a metronome. But because the motion of the leg is larger than the motion of the hand, what people would do is, so the goal is you want to raise your leg and your arm, and so they reach the height at the same time, the max height at the same time. So if you are going to the beat of a metronome, normal participants instinctively start raising their leg first, so that way they both reach the max height at the same time. Diabetic neuropathy patients would be off. They would move at the same time, and so max height of each limb would be at different times. Super weird study, but super interesting. And then the last one, Karen, is vision. Now, this is what humans utilize most. This is, if vision's available, vision A is the most important for us, and we'll rely on it if it's available. This is how vision works, right? We have our eyes, and then that information is transmitted to our occipital lobe, and then vision is processed. We know instinctively, just from observations, that vision is preferred because of the fact that when we're learning a motor skill, we look at what we're doing. So that instinctively tells us that we're clearly picking up the most from vision. There was this classic research called the moving room experiments, where they used children and then they also used adults. But what they would do is, do you see how the whole room is on a track? They would have the child turn around, and they would have the wall come in and out. And so touch and proprioception, because the room isn't moving, the wall is moving, right? So touch and proprioception would tell you you're stable, although vision will tell you that, oh my gosh, I'm like, something's coming close to me. The children all fell, even though the other two senses told them they were stable. Vision told them they were off. So it just proves that vision is primary. Does that make sense? So what research has looked at is looking at what humans are sort of focusing most in when we're performing different motor skills. And if we're comparing someone that is really good at a motor skill versus someone that is not, what is the difference on what they're looking at? And I've already sort of talked about this in other lectures, in that as you become better and better at a motor skill, you're very much more efficient at picking out what is the necessary things in the environment. So if we're comparing, yes, vision is the most important for everyone in motor skills, but people that are really good at a motor skill are better at using their vision because they can point out what is the most important. Whereas when you're new, you're sort of looking at everything and trying to figure out what's the most important from vision. Does that make sense? And they did this, and they do this now using these eye movement recorders. So it's, I don't know if you guys can see it, but it tracks foveal vision. So foveal vision is your central vision. So how your pupils are moving. It just looks at what you're looking at. So by comparing, so if you would look at a pro, their eyes would move less and in less areas because they're picking out the most important things, whereas an amateur would be like all over the place because they're trying to think and look at everything. Before this, what they would do is they would use occlusion techniques. So they would use these glasses that would like quickly black out vision. And so they would black out vision at different times of a motor skill and then seeing how it would affect performance. And if it affected performance the most, then clearly whatever happened right before there, it turned is the most important of what we're looking at. So let me show you this crazy video.
So Ronaldo's vast experience gives him the ability to intuitively read the game under normal conditions. But what if the conditions are very far from normal? Can Ronaldo still hit the back of the net if all the lights are turned off and he's in complete darkness?
Okay, what we're going to do, we're going to have Andy feeding the balls in as if it's a cross, and then sometime in the ball flight, the lights are going to go black, so you won't be able to see anything at all. We're expecting you to be able to put the ball in the goal. That's what we're hoping will happen. We're hoping that you'll have picked up some advanced cues from Andy's body position, the shapes, the positioning of his feet and his hips.
So this would be an
and
example
be able to
of
tell
temporal
exactly where the ball's
occlusion.
going to go and get yourself in the right position.
Yeah, I
even
know,
though you
eh?
can't see it.
Okay. Taking Ronaldo,
This has got to be like
seemingly
12 years old, 10 years
is an
old.
amateur footballer called Ronald.
Come and join me, Ronald. Ronaldo. So we've got Ronald in here, same age as you, roughly the same height. We're going to use Ronald as a comparison and see how he reacts doing this same test.
Ronald is going first.
Dark! Light!
So what does the night vision reveal? Ronald misses the ball by quite a way. Perhaps not that surprising. But can Ronaldo do any better?
I hope to do once.
Dark! Light!
Alright, that's one straight in the back.
The night vision replay shows how differently Ronaldo performs.
So do you see the difference where clearly
To confirm
the amount of vision was available was different? It was the same, sorry, between amateur and professional, but the professional is able to pick out more from vision in that short amount of time than the amateur, clearly.
And the replay?
How hard is that? It's difficult because it's changed a lot. Yeah. Because you are focusing the ball and after no light, you have to try to memorize the ball.
Human reaction time is about 200 milliseconds, and by 500 milliseconds, Ronaldo's subconscious has interpreted Andy's body language, worked out which direction the ball will go in, calculated its speed and trajectory, and then programmed his body to reach it at the optimum moment.
Stop that!
It's almost as if they're doing maths in their head, even though they wouldn't be able to describe it to you. You could see from their performance that Ronaldo saw the first part of the ball flight information. He picked up information from Andy kicking the ball and was able to move his body into the correct position. This is because he's processed the information. He has experience of where the ball is likely to go. He's able to analyze all that as it's coming towards him and therefore connect successfully with the ball.
Stop that!
Ronald, on the other hand, doesn't have the same level of experience. He would have watched the ball flight. It's likely that he would have just had his eyes on the ball instead of picking up any information from Andy himself. And then when the lights go down and it's black, he's kind of stranded in no man's land a little bit and just has to do his best to react, but is naturally going to struggle with that.
Yeah, poor Ronald. It continues on and they just keep showing how bad he is. But continue watching the video on your own time, or else we'll go over. But interesting, right? Does that make sense? How much the body is able to process? Is there a Discord or WhatsApp for this course? I think there's a WhatsApp group. I have a Discord over the NFTs. Oops. Okay. So before like those glasses or this technology that we talked about with like Ronaldo or the eye movement trackers, what they used to do way back in the day when these studies first started is that they would, like, here's an example of an event occlusion technique. So what they would do is here's a badminton example, and they would ask the badminton players, okay, so here's a video of someone doing badminton. Which way is the birdie going to go? And then they would black out certain parts. So the arm, the racket, the person's head, the lower body. What did they do on this side? I don't know, just right here. And look at whether their guesses of where the birdie was going to go would change or be wrong more of the time. And then clearly that's what people are looking at when they're performing motor skills. So these examples are just ways of trying to understand what people are picking out in the environment from vision when performing a motor skill. Does anyone understand what allowing what two eyes allows for versus one eye? So if you were to perform a motor skill and then have one eye closed, versus, you can still look and see, right? Yeah, so having two eyes, because two different angles, allows for better depth perception. So that's why we have two eyes. So that's going to be important for motor skills because it's going to allow us to judge distance better. That if we have one eye not available, we would be less accurate in our distance measurements. That's going to be important in completing motor skills, right? We have two fields of vision. We have central vision and peripheral vision. So central vision is what's tracked with those eye movement goggles. And the middle 2 to 5% or 2 to 5 degrees of our vision is what's called central vision. And that's what we do at focusing. So in performing motor skills, it gives us the most information in terms of providing like critical information. So if we're looking at a motor skill where you're reaching and grasping, central vision, we're going to focus at an object, and that's going to tell us distance and shape, size of what we're trying to grasp, and then that's going to be put into our motor skill. When we're moving, central vision stays on the path that we're trying to move. Our peripheral vision is used for picking up motion. So interestingly, because we have two fields of vision, it's like they believe that when humans evolved, when eyes evolved, there's two types of vision. Central vision, or picking up a small amount of a field of view, but picking out like really distinct details. And then peripheral is a wide range of vision, just picking out motion or things moving. They evolved together and it became, one eye. But peripheral vision, so when I focus on this cup, I'm looking at the click. So we're going to talk about different types of motor skills and what we notice next day. When people are reaching and grasping, they're focusing initially, and then at the end on the object they're reaching for. But your peripheral vision is always monitoring motion. It can pick up motion. So when you're walking on a pathway, you would look at the curb, but you'd be aware of things moving in the environment through your peripheral vision. And so when we talked about perception action coupling before, when we're timing and adjusting our movements based on what we're picking up in motion, our timing of movements is going to be based on our central vision, focusing in on different aspects of our environment that are important for that particular motor skill. This sounds super complicated. I just want to finish up this lecture. Our body's ability to time isn't processed. It is judged subconsciously through this sort of optical variable that they figured out called tau. Tau means time to contact. And so we're able to judge time to contact, or of an object coming close to us or us coming close to an object. We're able to time our movements because we're able to pick up the relative size of change of an object as it comes close to us or as we come close to it. So if you were making a video game and you wanted to make it look like an object is coming closer to you, you would slowly make that object look bigger and bigger and bigger and bigger. That gives you the sense of coming close, right? Or motion. That's what our eyes pick up. And that happens through central vision. So what they looked at with using these goggles is that when we are timing our movements with the environment, we at the last second are looking at that object with our central vision because it allows us to subconsciously judge time to contact. So that, again, is removing an amount of processing that's required from the brain. Any questions, anyone? Oh, did I screw this up? Yes. Oh, okay. So definitely, I know there's a lot of material. Try and run through the slides again, because I go into more detail with examples in the slide content. But go back and rewatch this lecture, and I'll highlight the main points or outline what are the main points of the lecture, and then you can use that as a backbone, get it or understand it, and then start adding in the stuff from the slides. One last little thing that I just skipped over was that one study looked at how much sort of time is available for us to be able to operate in a closed loop system. And it's about 100 to 160 milliseconds, a reaction time in a sense. If we want to be able to use feedback, we need at least 100 to 100 milliseconds. Okay, any other questions? Hopefully that was interesting for all of you. Cool. Definitely watch that Ronaldo video. Awesome. Okay, everyone. Have a good week. Oh, someone said something about discussing. But do we have classes going forward? Yes. Yep. So my class, you are no strike. Yes, I would imagine, Georgia, that everyone's heads is like so much information. Just let it. When you go through it, I promise you, you're gonna be like, oh, that just makes sense. Oh, that makes sense. Oh, that makes sense. It's just a lot, so it's overwhelming. But once you go through it and you start organizing it into just the components of the outline of the lecture, it'll feel like not that much information. Promise. Bye, everyone. Have a good week, okay? Have fun in your labs, too.